Hey guys, welcome to the next lesson. And today we're going to talk about areas and polar curves. And our story begins with a circle with what's known as a sector, right? So a sector is basically a pizza slice out of your circle. And you may or may not know the formula for the area of a sector. But if you don't know it, it should be easy to develop it actually, because we all know what the area of the entire circle is. By the way, that's the center of the circle. There's a radius. But the area of the entire circle, of course, we know that, right? So I know that the area of the sector is going to be some multiple of the area of the circle, some fractional multiple, because I have a piece of the entire circle here. Obviously, if we did this, we'd get too much area, we get the whole circle, right? So we have a piece of that circle. Well, how much of the circle do we have? Well, if we went all the way around with our theta, then our sector would be made up of the entire circle, right? But here, we're not going all the way around. We're not going 2 pi radians. We're going theta out of 2 pi radians, I guess. So the area of the sector would be this fraction, theta over 2 pi, times the area of the entire circle. So this is the piece of the circle, theta out of 2 pi, times the area of the circle. And of course, the pi's cancel. And the formula for the area of a sector, the area of a pizza slice of your circle, within your circle, is just going to be what? 1/2 theta r squared. Again, a formula you may or may not have been familiar with, but you could easily figure out. So we're going to use this to help us find the areas involving polar curves. So over here, let's say what I have is this leaf of a rose curve. And we want to find the area, let's say, within the entire leaf. Well, we can think of that area being made up of a bunch of circular sectors like this, but very small sectors. So let's say at this point on the polar curve right here, right? I could do a sector, a very tiny sector, circular sector here, very tiny one. I could find the area of that tiny sector, and then I could sum up a whole bunch of tiny sectors to estimate the area within this leaf. So the sector is analogous to the rectangle when we were looking at areas under a curve, right? It's the same exact concept. But really the way I want you to think of this is the following way. I'm going to give you the formula for how we find the area in a second. But conceptually, this is what we're doing. So let's say that, I don't know, let's say this is like a pi over 6 angle here, right? So I draw a pi over 6 angle with a straight line segment like that. If, let's say, the curve begins here when theta is 0, and then it moves like this until we get to theta equals pi over 6. So let's say that's the case for this particular polar curve as an example. So we start here, let's say, at theta equals 0, and we rotate to pi over 6. You now have created an area which looks like this. And when we use the formula that I'm about to give you, I could find the area of that piece of the leaf if I go to pi over 6. If I went to pi over 4 instead, from 0 to pi over 4, then perhaps, it depends on the geometry of the leaf itself, but let's say that's exactly half the leaf. I could get area of half the leaf if I went from 0 to pi over 4, so now I would have this much area. But of course, we'd have to keep rotating if I wanted to get the area of the entire leaf. So to get the area of the entire leaf, right, I could go a little further to here and then all the way to here. And let's just say, I don't know if it's true for every leaf. It's obviously is not true for every leaf. But let's say for this one, it's true that when we get to pi over 2, we return to the pole. If that's the case, we return to the pole at pi over 2. If I rotate from 0 to pi over 2 with my radii, then I will realize the area of the entire leaf. But I just want you to get a feel for how that area is built, right? So if I only go this far, I'm getting this area. If I go this far, I'm getting this one. If I went this far, I'd be getting this much area. But if I rotated until my angle came back to the pole here, then I would realize the area of the entire leaf. Okay, So when I was drawing this very tiny sector before, we want to think of the angle as being that very small movement. So that's going to be our d theta in our formula for the area of a polar curve. So let's get right to the formula now. We're going to say if we define a polar curve, r equals f of theta, and let's say we want to go from alpha to beta, I guess we can use or equal to signs there. Then the area between the origin and the curve what do we call it? The pole, actually. The pole, or the origin. The area between the pole and the curve is going to be this. So we're going to say A equals the integral from alpha to beta of 1/2 r squared d theta. So there's our 1/2 r squared theta, where the d theta is that slight change in the angle, resulting in this formula right here. So the area between the pole, or the origin, and the curve. So if I only rotated this far, starting at theta equals 0 to theta equals pi over 6, it's giving us this area here, that section right there. All right, so this is the easy formula we're going to use to find areas involving polar curves. So let's jump into our first example. So example 1 says find the area inside one leaf of r equals cosine 2 theta. So based on the way they write the question here, we know that this is a rose curve that we're dealing with. And we can graph it easily, right? Let's first take a look at y equals cosine 2x. We know the midline is going to be the x-axis here. We know the period is going to be pi, right? 2 pi over b, so 2 pi over 2. So the period is going to be pi. I'll cut pi in half to get pi over 2. I'll cut pi over 2 in half to get pi over 4. 1 pi over 4, 2 pi over 4, 3 pi over 4. It's a cosine wave, so we're thinking this shape. Its amplitude is 1, so we go up to 1, we go down to -1. So we begin here, we end here after one period of pi. Right in the center of that period at pi over 2, that's when we're at the minimum. We'll cross the midline here and here. All right, so simple cosine curve looking like this. There's your cosine of 2x. Okay, now we're ready to graph the polar version. And we know it's some sort of a rose curve that we're going to end up with here. Okay, so when the angle is 0, we're at a radius of 1. So when I'm pointing in this direction, we're here. So that's where we are when theta equals 0. We're going to rotate to the pole here. So when we get to pi over 4, I guess we're going to be at the pole. At pi over 2, we're at -1. So at pi over 2, that's here, right? We're going to be pointing in the opposite direction, so here at -1. So it's going to do this, rotating counterclockwise to here. We're going to have a return to the pole here, right? So we had a pole here, and now we have our second return to the pole here. So it's going to rotate like this. When we get to pi, we're going to be at 1. So pi, pointing in this direction, we're going to be here. So it's rotating. So notice it's moving in this direction like this. Came back around like this. And now it's going to rotate to here. Now, of course, this is not a full rose curve. So it looks like I have to go further than pi to realize this curve. So on our standard curve, I guess, we'll just go further. 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, otherwise known as 3 pi over 2, 7 pi over 4, and then 2 pi. But of course, this is going to repeat, so it'll have a maximum here and a maximum here, minimum right in between at 3 pi over 2. It'll cross here, it'll cross here. All right, so let's finish off our rose curve. So we just left off at pi, so now we're going to return to the pole here. So another return to the pole here. Rotating counterclockwise. And now at 3 pi over 2, we're at -1. So 3 pi over 2 is pointing this way, but -1 makes us point up this way. So we're going to keep rotating counterclockwise, and we're going to end up here. At 7 pi over 4, we're going to return to the pole. So we're here. So we have added this movement here, going like this. And then, yeah, we return to the pole. And now at 2 pi, we're back at 1. So we complete this curve, which ends up having 4 leaves, looking like that. So that's our graph of r is equal to cosine 2 theta. We want to find the area inside 1 leaf of that curve. Okay, so let's think about how we're going to find the area within 1 leaf. When I was at 0, I was right here. That's where we started. And then we rotated this far to get here, right? And when we do that, we realize, okay, if I rotate this far, I get this area. This far, I get this area. But if I rotate back to the pole, I will get this area here. So that area right there that I've shaded, which is half of a leaf, right, because of the symmetry, is going to be the integral from 0 to something. And that something is going to be whatever angle we were at when we returned to the pole, right? Well, what was that angle? Was that pi over 4, I think, right? Does that sound right? Because if I plug in pi over 4, I'm taking the cosine of 2 pi over 4, the pi over 2, and the cosine of pi over 2 is indeed 0, right? So that's pi over 4. So we came to the pole here when theta was pi over 4. So if I did the integral from 0 to pi over 4 of my 1/2 r squared d theta, that will give me the area of half a leaf. So if it's 1 full leaf I want, I'm just going to double that area right there. So let's create our expression here. First of all, it is the integral from alpha to beta of 1/2 r squared d theta. So that's your formula that we're going to use. So in our case, the area of 1 leaf, that's what we're finding here, will be equal to, okay, the integral from 0 to pi over 4, but that'll just give us half a leaf. So we're going to double that. So we'll say 2 times the area from 0 to pi over 4 of 1/2 r squared d theta. Well, r is this. So it's cosine squared 2 theta. There's my r squared, and then d theta. So that's how we set this one up. So we're going to just plug in r, which is cosine 2 theta. So we have our cosine squared 2 theta. This 1/2 can come out of the integral, multiplying the 2, giving me a 1 there. So the area here is going to be the integral from 0 to pi over 4 of cosine squared 2 theta. And at this point, you probably recall that to get this, right, we needed those identities, right? So if I do that real quick over here, we know cosine squared theta minus sine squared theta equals cosine 2 theta. We know if I add the cosine squared theta and sine squared theta, we get 1. It's a cosine squared that I want to replace here, so I'm going to add these together to get 2 cosine squared theta equals 1 plus cosine 2 theta. And that's the identity I'm going to use here, right? I probably shouldn't have used theta here, though. I'm going to use a different variable here. It's going to make it easier for us to make the translation to what we need. So let's call it x, I guess. So cosine squared x minus sine squared x equals cosine of 2x. Cosine squared x plus sine squared x equals 1. So 2 cosine squared x equals 1 plus cosine 2x. Looks like cosine squared x. Cosine of 2x. So I know this is my relationship. So I also know that cosine squared x is equal to 1/2 times 1 plus cosine 2x. And that's typically what we would replace if I had a cosine squared of x. But here I have a cosine squared of 2 theta. So what I'm going to replace that with is this. So we have the integral from 0 to pi over 4 of 1/2 times 1 plus, well, cosine 2x, if I'm taking the cosine squared of x, well, here I'm taking the cosine squared of 2 theta. So it's going to be 1 plus cosine of 2 times 2 theta. So that's 1 plus cosine 4 theta. And then, of course, our d theta, which I forgot to write here. So there it is. And this is something we can do. So let's do it. I'm going to pull the 1/2 out. So 1/2 times the integral from 0 to pi over 4 of 1 plus cosine 4 theta d theta. And now I'll integrate. So I have 1/2. This just is going to be theta here. But here, the antiderivative of cosine is going to be negative sine, but it's a 4 theta there, right? So that's going to be minus sine 4 theta. Oh, sorry, positive, not minus. It's the antiderivative. So positive sine 4 theta over 4, evaluated from 0 to pi over 4. So my area is going to be 1/2 of pi over 4 plus sine of 4 times pi over 4, instead of, in other words, sine of pi over 4, minus 0 plus the sine of 0 over 4. So that is going to turn into a whole bunch of 0 there. So the area here for one leaf turns out to be 1/2 times pi over 4 plus, well, this is 0, so it is just 1/2 times pi over 4. So the area of one leaf turns out to be pi over 8. So there it is, the area of one leaf. We have to do a little bit of manipulation to get our answer analytically here using this idea over here that we've seen before. But the area of one leaf of this rose is pi over 8. Okay, a couple more examples coming your way next. Okay, so our next example here is find the area inside the circle, r equals 1, and outside the cardioid, r equals 1 minus cosine theta. All right, so this involves two different polar curves. One of them is a very simple circle, r equals 1. And we can sketch that one pretty easily, I think. So let's do this. 1, negative 1, 1, negative 1. Okay, so for the circle r equals 1, when the angle is 0, the radius is 1. When the angle is pi over 4, the radius is 1. So here, maybe. When the angle is pi over 2, the radius is 1. When the angle is pi, the radius is 1. When the angle is 3 pi over 2, the radius is 1. So this is the circle. Simple, but pay attention to where we are on the path at different measures of theta, or different values of theta. So pay attention to that. That's going to be important. Like, when were we here? We were there when theta was 0. When were we here? When theta was pi over 2. And so on. So we need to keep that in mind for these polar curves that we're drawing here. All right, r equals 1 minus cosine theta. Once again, we should be able to do that pretty easily. That's the same thing as y equals negative cosine x plus 1. All right. The midline is y equals 1. The amplitude is going to be 1 here, so it's going to go up to 2, down to 0, so it's going to oscillate between 0 and 2. Since the a value is negative, it's going to be a cosine curve that looks like this. The period is going to be 2 pi, since we're doing cosine of 1x here, so the period is 2 pi. All right, so by the time I get to 2 pi, I will complete this wave. Half of 2 pi is pi, half of pi is pi over 2, 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2. Okay, so this will be at its minimum, which will be here at the beginning of that first cycle and at the end of that first cycle. It'll be at its maximum right in between here. It'll cross the midline at pi over 2 and also at 3 pi over 2. All right, so there's the easy graph of y equals negative cosine x plus 1. Let's see if we can use it to graph this cardioid, r equals 1 minus cosine theta. So it starts at the pole, right? So we're here when theta is 0. So we're going to be here when theta is 0 for our cardioid. At pi over 2, we're at 1. So at pi over 2, we're at 1. Here's 1, so we're going to be here. So this cardioid is going to rotate counterclockwise to this value, or that location. And then at pi, we're at 2. So pi, we're at 2. So I got to make my x-axis, sorry, my y-axis, no, I was right the first time. My x-axis a little longer. Negative 1, negative 2, okay. Because I need that radius to be 2 when I'm at the angle of pi. So when I'm at the angle of pi, I want that radius of 2, so we're going to be here. So this is a cardioid, right? So it rotates out. It's a wide-looking graph, so it's going to do this. So that's what it looks like so far. And then at 3 pi over 2, we're at 1. So 3 pi over 2, we're going to be a distance of 1, so we're here. And again, we're going to rotate counterclockwise again in a wide kind of fashion here. And then we're going to return to the pole when we get to 2 pi. So our cardioid looks like this. All right, so we have our circle. We have our cardioid. So here is r is equal to 1 minus cosine theta, that is. And then our circle, of course, was r equals 1 And what are they asking for here? They want the area inside the circle and outside the cardioid. So inside the circle, outside the cardioid. So that's this really cool looking shape over here. And that is what we want to find the area of, this shape right here. Now, you probably recall when we were doing normal area problems, we would do a lot of outer area minus inner area kind of things. And it turns out you can do that kind of concept sometimes with polar curves, including with this example. But it's all about whether the curves are sweeping together or not. And in this case, I think they are sweeping together. You'll see what I mean by that in a second. So this cardioid is here when theta is 0. At pi over 2, that's when it was 1. So this is important that you realize. So try to watch me here as I try to do this. So as this circle is moving and theta is increasing, this cardioid is also moving. And they move like this. And they both come to this place when theta is pi over 2. So again, they're sweeping together. Now that's going to be important because we can think of like a representative sector, right? Maybe like one drawn here-ish or something. So if I want this area, it's going to be the big sector minus the little sector. But this is a concept we can only use when the curves are sweeping together, which they're not always doing. But here they are. So I can do that. Outer sector minus inner sector to get that area that I want. Okay, so let's see if we can set up the integral to find this area. So the area that we seek here is going to be, well, first of all, I am going to do all the sectors from theta equals 0 to theta equals pi over 2. And I'm going to do that subtraction of larger sector minus smaller sector. Right? We have the smaller sectors here, the larger ones here. I'm going to do that from 0 to pi over 2. But when I do, I'm just going to get half the area we seek. So I know I'm going to have to double what I'm doing here. So I'm going to do 2 times the integral from 0 to pi over 4. No, sorry, pi over 2. That's when we reach that. 0 to pi over 2 of, okay, the outer sector is going to be a 1/2 r squared. So that's going to be 1/2 of 1 squared. So there's your outer sector. The sector is created by the circle. But then these inner sectors, these smaller sectors, are going to be created by the cardioid right here. So minus 1/2 times 1 minus cosine theta squared, and the whole thing d theta. And this setup will work here, right? Okay, so let's see if we can navigate our way through. Obviously, you should focus on the fact that we set it up this way, and you can come up with the setup. That's the key to these. The rest of this is just plain old math, actually. So let's do the plain old math part. So 2 times the integral from 0 to pi over 2 of, what do we got here? 1/2, and then minus 1/2. Whoops, can't distribute that 1/2 across there. Okay, minus 1/2, and then we'll expand this. So 1 and then minus 2 cosine theta, I guess, and then plus cosine squared theta over here, d theta. I need another bracket there. Okay, so something like this. Okay, so we have a is equal to, I guess we can factor out this 1/2 multiple. Why don't we do that? Because then it'll cancel with this 2. So we have the integral from 0 to pi over 2 of just 1, so I'm factoring the 1/2 out, I guess. 1 minus this stuff right here. 1 minus 2 cosine theta plus cosine squared theta. And all of this d theta. Okay, so we have the area is going to be the integral from 0 to pi over 2 of, all right, 1 minus 1 is 0. And then this negative 1 is going to distribute across the other stuff. So that's a positive 2 cosine theta and then a minus cosine squared theta. We want to integrate this term by term, but I have this cosine squared theta. We know what to do with that, right? The cosine squared theta. We could use the identities, but what did it turn out to be? I think it was 1/2 and then times 1 plus cosine 2 theta. I'm pretty sure that was right. And so we have the area here is going to be the integral from 0 to pi over 2 times 2 cosine theta minus, and then we'll substitute for this, except I'll use the distributed version, distributing 1/2 across. So minus 1/2 plus 1/2 cosine 2 theta d theta. All right, so we have a is equal to the integral from 0 to pi over 2 of 2 cosine theta minus 1/2 minus 1/2 cosine 2 theta d theta. All right, so I think we're ready to find those antiderivatives term by term. So let's do that next. So the area here is, okay, so the antiderivative of 2 cosine theta is just going to be 2 sine theta. And then we have minus 1/2 theta. And then here we have minus 1/2. The antiderivative there is going to be what? Sine 2 theta over 2, or 1/2 sine 2 theta. So we have another 1/2, and then sine 2 theta. And we're going to evaluate all of this from 0 to pi over 2. So our area here is going to be 2 sine of pi over 2 minus 1/2 times pi over 2 minus 1/4 times the sine of twice pi over 2, in other words, pi. And then minus the subtraction of plugging in 0. Now, if I plug in 0, the sine of 0 is 0. That 0 also, the sine of 2 theta is also going to be 0. So that is going to be a whole bunch of 0. I'm taking a shortcut because I'm running out of board space, as you can see here. So we have 2 times the sine of pi over 2. That's 2. 2 times 1. And then minus 1/2 times pi over 2. That's pi over 4. And the sine of pi is just 0. So it turns out that I think that's going to be our answer here. The area of this really cool looking region is exactly 2 minus pi over 4. Okay, I do want to show you an alternate approach to this very same problem. So let's take a look. Okay, so an alternative approach to doing the same problem we just did. Instead of doing the outer sector minus the inner sector, which again we can only do if curves sweep together, we could have done this. We could have gotten the area of the semicircle, which is a little bit too much area, right? So we could have started with that, the area of the semicircle, and then subtracted something from it. So I could do the area of the semicircle minus something, and that something is going to be this area here. So how can I get this area here? Well, if I just focus on this half of it, I know with the cardioid, and the cardioid started here when theta was 0, and then it got here when theta was pi over 2, right? So if I'm rotating through, I can rotate this far, and then this far, and then this far. But if I get to the angle pi over 2, I will realize this area right here. So that area right there that I just shaded would be some sort of integral of 0 to pi over 2 of 1/2 with the r squared from the cardioid, which I guess is 1 minus cosine theta for r. And that integral would give us this area. So if I get the semicircle, I could subtract twice that, and that will give us the right answer also, right? So the setup would be the area of the semicircle minus 2 times the integral from 0 to pi over 2 of 1/2 r squared, where we're looking at the cardioid. So the cardioid's equation is r is equal to 1 minus cosine theta. So 1/2 1 minus cosine theta squared d theta. And the area of the semicircle is pretty straightforward, right? We just have a radius of 1. So pi r squared would be the full circle. So that would be pi. So half of this circle would be pi over 2. So if you did the area of the region you want, which is this with the dots right here, that area, you could get it by doing pi over 2 minus twice the integral from 0 to pi over 2 of 1/2 1 minus cosine theta squared d theta. And I'm not going to work it out, but if I did, I get the same exact answer we got before, because this is another way of getting the same area. Now, the reason I'm showing you an alternative approach is because when you're working with two polar curves, they don't always sweep together. In fact, let's take a look at this example, example 3. So this example says, find the area shared by the cardioids r equals 2 times 1 plus cosine theta and r equals 2 times 1 minus cosine theta. All right, so let's do these one at a time. The first one is what? Y equals 2 plus 2 cosine theta, or 2 cosine theta plus 2. So I'll write it as 2 cosine x plus 2. And I'll do my really quick graph here. Midline at y equals 2. Amplitude of 2, so this is going to go up to 4 and down to 0. So it's going to oscillate between 0 and 4. It's a cosine wave, so it looks like this. The period is 2 pi. All right, so 2 pi, f of 2 pi is pi. F of pi is pi over 2, 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2. Okay, so that's the shape. Maximum here, minimum here, crossing the midline here, crossing the midline here. So, okay, so this is the graph of y equals 2 cosine x plus 2. So I'm going to use it to graph this polar curve. So when we're at the angle of 0, we're out here at 4. When we're at pi over 2, we're at 2. So this is the value 2. So pi over 2, we're at 2. And then we're going to return, or we're going to not return, but get to the pole for the first time, I guess, when we're at pi. So this is a cardioid, so it is going to sweep wide like this, counterclockwise rotation, and then reach the pole right there. At 3 pi over 2, we're at 2. So 3 pi over 2, we're here. So we're going to continue to rotate counterclockwise. And then we go to the angle of 2 pi, pointing straight to the right, where the radius is 4. So we're going to return to that point. All right, so this is the cardioid for r equals 2 times 1 plus cosine theta. Now let's take a look at this one. And that would be what? Y equals 2 minus 2 cosine x, I guess. So we'll say minus 2 cosine x plus 2. So this also has a midline at y equals 2. It also has an amplitude of 2. So it's going to go up to 4 and down to 0. However, its a value is negative. So it's going to have this shape to it instead. And the period is 2 pi, since we're doing the cosine of 1x. All right, so 2 pi, f of 2 pi is pi, f of pi is pi over 2, 1 pi over 2, 2 pi over 2, 3 pi over 2. All right, we graph this shape. It's at a minimum here and here. It's at its maximum here. It crosses the midline here and here. Okay. All right, so there's the curve. All right, so this curve is going to start at the pole, this cardioid. And at pi over 2, it's going to be 2. So pi over 2 is going to be 2. And at pi, it's going to be 4. So we're pointing here, it's going to be 4, so it's going to be here. So this is rotating counterclockwise like this. Come here. And then 3 pi over 2, we're at 2. So 3 pi over 2, we're at 2. So it's here. And then it's going to come back to the pole here. So it's going to swing wide like this. A little wider than that. And then back to the pole like this. So we have two cardioids that share some area. I guess this is in honor of upcoming Valentine's Day, right? So you can make a card for your special person, I guess, for Valentine's Day. You can make a card that looks like this, and you can say, hey, this is how much we share. And not only is that how much we share, I'm going to calculate what that is just for you. That's the area we seek here. So we have these two cardioids, but notice they don't sweep together, right? So this one kind of started here, right? And then it swept like this, I guess. And then, let's see, is that right? Am I doing that right? Let's see. Well, you know what? It doesn't matter if they sweep together or not here, because we're not getting like an outer area minus an inner area anyway, right? So we're definitely not going to do outer sector minus inner sector for an area like this. So how do we figure out an area like this? Okay, well, what we can do is perhaps focus on one of the two cardioids. Maybe I'll focus on the blue one, r equals 2 times 1 minus cosine theta. Because I know as I sweep with my radii through this, if I go from here, and I think when we were at 0 on the blue one, we were at the pole, right? And then when we got to pi over 2, we were at 2. So on the blue curve, we were here when theta was 0, and then we were here when theta was pi over 2. So if I can rotate my angle this much, and then this much, and this much, and then eventually get to pi over 2, then I'm going to get this area right here. And from the picture, we can see that this area that I'm shading in here, that we would get if we rotated from 0 to pi over 2 on the blue cardioid, we would get 1/4 of the area we seek. So the area we seek here is going to be 4 times that area right there. Okay, so let's take a look. This is going to be the area is equal to 4 times the integral from 0 to pi over 2 of 1/2 r squared. Well, this is the blue curve we're working off of, so it's going to be 2 times 1 minus cosine theta. There's your r. We want to square it, so don't forget to square your r. And there we have it. So this is going to be the setup for this integral. 4 times this area. Okay, so let's work it out. So we have a is equal to 4 times, let's see, 1/2 can be pulled out. So 1/2 times 4 is 2. So we'll pull that out. So it's 2 times the integral from 0 to pi over 2 of, okay, this is what, 2 minus 2 cosine theta being squared d theta. So it's going to be 2 times the integral from 0 to pi over 2 of, okay, expanding this now, so 4 minus 4 cosine theta plus 4, did I do that right? Outside I have, let's see, I don't think I did it right. 2, 4, that's minus 4, so it should be minus 8, right? So this is minus 8 cosine theta, and then plus 4 cosine squared theta, d theta. So we have 2 times this integral right here, so 0 to pi over 2 of 4 minus 8 cosine theta plus 4. Well, there's our friend cosine squared again. What was that? 1/2 plus 1/2 cosine 2 theta, I'm pretty sure. And all of this d theta. So that area here is going to be 2 times the integral from 0 to pi over 2 of, alrighty, 4 minus 8 cosine theta plus 2 cosine 2 theta d theta. So it's going to be 2 times the integral from 0 to pi over 2 of 4 plus 2 is 6. So what? 6 minus 8 cosine theta plus 2 cosine 2 theta d theta. Okay, so we're ready to do antiderivatives. So the area is going to be, that's just going to be, well, 2 times, 2 there, can't forget that, 2 times 6 theta, and then minus 8 cosine theta, so that's going to be what, minus 8 sine theta, antiderivative. And then over here, antiderivative cosine 2 theta, that's going to be sine 2 theta over 2, and multiplying that 2, it's just going to be sine 2 theta, so positive sine 2 theta. And we're evaluating from 0 to pi over 2. I know when I plug in 0, that's 0, that's 0, that's 0. So that's going to be a whole bunch of 0, thankfully. So 2 times 6 times pi over 2 minus 8 times the sine of pi over 2 plus the sine of twice pi over 2, that's the sine of pi. And then minus a whole bunch of 0. I'll just squeeze in that minus 0 over there. Okay, so the area is going to be twice. 6 times pi over 2 is pi over, no, is 3 pi. So 3 pi. And then minus 8 times 1, right? So minus 8, and then plus sine of pi, so that's 0. And then I'm going to double that, so 2 times that. So 6 pi minus 16. So this area that the two hearts share is 6 pi minus 16. So when you make this Valentine's Day card, you can say, we share so much. And when your beloved asks you, well, how much do we share? You say, 6 pi minus 16.